Okay. So my main research focuses towards connecting fitness locations with other subcategories of locations with and without network analytics. But in order to cut it short, in today's presentation, I will mainly focus on the methods I have used that contain network analytics. The title of the presentation is Identifying Complementarities and Substitutabilities of Physical Exercise through Network Analytics. Interventions that are typically studied for promoting physical exercise contain the limitations of possibly not being able to generalize well due to small sample sizes and may contain sampling biases depending on the participants. Even though these issues can be partially addressed with more participants, the long-term carryover effects on the behavior change are difficult to be obtained. Determining effective strategies for promoting physical exercise can be enhanced by understanding habitual patterns shared among active individuals. Utilizing human mobility data can be an effective way of exploring active users and differentiating their visitation patterns with non-active ones. My dataset captures only the United States, and according to Subgraph, describes approximately 6 to 8% of the devices in the US. There are data for 9 months from September 2019 to June 2020, so there is some overlap with COVID. Each day contains approximately 55 million rows of visits. Each row is a visit from a user. I kept only the most interesting columns in this figure, but there are also information about the address, city, and state of the location, and also the UTC timestamp. Additionally, as we can see in this figure, for each entry, you have the local timestamp, the ID of the device, the location name of the visit, the top category, and the subcategory of the location. Also, you have the minimum duration time of the visit. To see an example, we can use a circled user. At 9:07 in the night, there's a visit at the home of the user for at least 12 hours. At 11 in the morning, the user visited a beverage bar for almost 2 hours. And at 8:30 in the night, he visited a general automotive repair for half an hour. To obtain the visits to fitness locations, I used the subcategory fitness and recreational sports centers, which for February 24, 2020, these 5 were the most visited locations. Data explorations on the visits dataset show that we can detect patterns that totally make sense to be observed for active individuals. This means that we can unveil more complicated relations between fitness locations and other subcategories of locations that we are unaware of their existence. An interesting observation can be seen in this figure, which is very logical and is an indication that the dataset contains interesting information. First of all, we deduce that the finding is independent of whether the user have exercised today, which is the figure on the left, or not exercised today, which is the figure on the right. The more a user visits a fitness location throughout the week, it's more likely the visits to diet and weight reducing centers are reduced. However, this figure does not prove a causation, but shows a correlation. It might also indicate a causation, but users that visit the gym more often could be people that have been doing it for years, or could be people that work in these locations so that they would need the weight reducing centers less. In this figure, we observe that more active users tend to visit snacks and non-alcoholic beverage bars like Starbucks more. The x-axis denotes how many days in the week a user has exercised. This finding is independent of whether a user has exercised today, which is the red line, or not exercised today, which is the blue line. So this finding might indicate that an active person tend to be more social by visiting these kind of locations. This figure shows the local time of users that have visited the fitness location. The color of each figure indicates how many times in the week the group has visited the fitness locations. When users are more active throughout the week, it seems that there is also a peak in the morning at around 10 a.m., which could show that either exercise is more habitual for them, or that more active users like to visit the gym in the morning hours as well, except from the afternoon. So in order to unravel potentially hidden patterns, I decided to deploy network analytics. I will explain now how I have created some of the most interesting networks from my trials and show some example results. Initially, I created a list of the co-visits per user. Here are 5 examples from all the users. For example, the first user has visited today a full-service restaurant and a used merchandise store. Then we remove the users who have visited only locations from one subcategory in the whole day, like the second user, because that conveys no information about the relationship between different locations or different subcategories, let's say. Then I create a dictionary that contains the number of all pairwise co-visits among all different subcategory of locations. These are 2 examples. The new car dealers with the fitness centers contained approximately 13,000 co-visits, and the limited service restaurants, these are something like fast food restaurants, with the full service restaurants contained approximately 434,000 co-visits. Using these, I create a graph in which the nodes are the subcategories and the edges contain the weight of the pairwise co-visits among the nodes. This is an example of a very small subgraph containing only 3 subcategories from the 294 that existed on February 24th. With this graph, the edges indicate something like the importance existing between those subcategories. Here are some interesting summary results about the graph. The 4 most co-visited subcategories out of 294 account for 56.4% of the total co-visits, and the 55 most co-visited subcategories account for 99.2% of the total co-visits. Fitness locations are the 6th most co-visited subcategory with approximately 1,700,000 co-visits. And the total number of co-visits on February 24th was approximately 17 million, but these are not the actual visits, just the co-visits. The first algorithm I have used for analyzing the results of the graph was Node2Vec. It is an algorithm for graphs which performs a similar process like the Word2Vec in natural language processing. It obtains for each node, so in our case for each subcategory, a vector in the latent space with the requested dimensions. It uses stochastic gradient descent, which maximizes the likelihood of preserving network neighborhoods of nodes. It uses breadth-first search to capture homophily, so common neighbors, and depth-first search to capture structural equivalence, so the structure of the network, in our case, based on the co-visits among them. We can choose whether to bias towards one of the 2 and how much. By having a vector for each subcategory, we can query the cosine similarity among different subcategories. I kept the same weight for homophily and structural equivalence, so I believe that the output of the Node2Vec indicate the subcategories in which the users visiting fitness locations behave similarly with the users of these subcategories. The table shows the results of one run, which took approximately 2 hours on my laptop. I believe that it makes sense for beauty salons and pharmacies and drugstores to be first and second, because it might mean that it's people taking care of themselves and their bodies. Because these are the outputs of a model working with stochastic gradient descent and a neural network, there is some randomness, so I cannot be certain that this is actually the meaning of and correct output. Full service restaurants and non-alcoholic beverage bars are subcategories that were loved by active users, so their high ranking might be because of the homophily. I'm not very sure of what to extract from the gasoline stations and with convenience stores, but I can perform some checks to obtain if the co-visits were obtained exactly before or exactly after visiting the fitness location, which might mean the active users combine their visit with visiting a gasoline station. With the weight being the co-visits, the weights indicate importance. In order to use algorithms like the shortest distance, which require the weight as cost, I change all the weights to be 1 over weight. Now, all the weights are between 0 and 1. What the new graph offers is that we can now query the shortest distance of a subcategory from fitness locations, even if we do not have any co-visits among them. As it was expected, the distances among locations are very biased towards the bigger subcategories. For example, the full service restaurants is the largest subcategory, So almost every location have their shortest distance towards that. This means that the full service restaurants are an important subcategory in general, but not necessarily more important specifically for fitness locations. In order to avoid this bias, the next graph I have derived is the importance graph, which is a directed graph. I normalize the weights leaving each subcategory so that their sum is equal to 1, so that the bias towards bigger locations gets reduced. Let's see an example in the next slide. So I have created this example for illustration purposes. These are not the actual values. So in the first figure, we are assuming that the co-visits between fitness and restaurants are 70, and also between fitness and parks is 30, which are these two weights. We want to create the importance graph, which basically normalizes the values so that the sum of weights leaving each node sums up to 1. For example, fitness gives 0.3 to nature and 0.7 to restaurants. So in order to obtain how important fitness is for the other subcategories, we need to check the other direction, how much importance the other location gives to fitness. In this case, fitness receives 0.75 from parks and also receives 0.875 from full service restaurants. Now, when we are comparing on how important fitness is for other subcategories, there is no bias at all towards the large subcategories, because the large subcategories are equally important to those locations. So this is an example on the actual data, using the subgraph containing only these 3 nodes. Even though there are much more co-visits between fitness and restaurants than fitness and nature, which is approximately 1/4 in total, the importance given towards fitness locations from these locations are almost identical. You can see that it's 0.039 and 0.038. Sorry, you can see that it's 0.06 and 0.061. Of course, in the actual network, there are 291 more locations that are connected with these 3 nodes. So the results cannot be explained just by looking at these 3 nodes. But we can just see that more co-visits that does not show that it's equal importance. These are the importance scores given to fitness locations from other subcategories. I have inserted the total co-visits that each category had and the 95% confidence intervals. We can see that most of these subcategories do not contain reliable results. For example, the water supply and irrigation systems had only 6 co-visits with all other subcategories, and only 1 was for fitness. So in order to obtain reliable results, I believe it makes more sense to discard locations with total co-visits less than a specific number. By choosing that number to be 300, here are the updated results. Now, the results are more reliable and contain a smaller interval of confidence. You can see that the results make more sense. For example, the subcategory sports and recreation instruction encapsulated 2 locations, a swimming school and a school of martial arts, which makes sense to be very similar or co-visited with people visiting fitness locations. There are 335 total co-visits, which is more than the 268 visits, because a single visit can create more than 1 co-visit. Also, people that visit fitness locations tend to co-visit in the same day meat markets, which also makes sense. Still, I am not very confident if when ordering the subcategories, I need to focus more on the actual percentage, or if I need to concentrate on the total co-visits that the subcategory had. For example, is a meat market that comes 3rd but only has approximately 1,000 co-visits more important? Or is snack and non-alcoholic beverage bar that scores 13th but with much more co-visits more important? Moving on to another technique I have tried, now I focus on co-visits per user instead of co-visits per subcategory. This avoids the dominance method that the previous technique contained. An additional co-visit on the same day now does not impact the importance of another co-visit. For example, if a user visited 4 subcategories on a specific day, Each of the 4 contain 3 co-visits in total. So querying on the importance of one with another would give 1/3 importance with the previous method. However, this new per user method would give a value of 1 for all these subcategories. The less the number of co-visits in the same day, the closer these 2 values will be. To create results for this technique, I first create what can be seen in this figure. Each row corresponds to a user and each column corresponds to a subcategory. For example, the first column is representing the subcategory pet and pet supply stores. For each user, I built a 1 × 294 vector with 1 if they have visited a particular subcategory on a single day and 0 if they did not. I keep only the users that visited at least 2 subcategories in that day. Then I want to build the vector for a specific subcategory. In order to do that, I keep only the users that visited that subcategory. For example, when we choose subcategory pet and pet supply store, I keep all users in which there is 1 on the first column. Then I average on all other columns. To give an example of that, let's look at the third column and assume we only had these 5 rows. The output of the third value in the vector of that particular subcategory would be 1 + 1 divided by the 5 users, so 0.4. This is done for all columns, so for all subcategories. For querying the cosine similarity between 2 subcategories, we calculate the cosine similarity between their vectors. These are the top 10 results by sorting on the cosine similarity. I believe that what this method actually calculates is how the visits of subcategory X and the visits of subcategory Y correlate. So I tend to believe that these are subcategories that their users follow similar visitation patterns with the fitness visits. Now we have results based on 3 different approaches I have explained, which all calculate something very similar. Column 1 is the cosine similarity per user that I just explained. Column 2 are the results of the node to vec model. And column 3 are the results from the importance model that ignores how popular a subcategory is in general. For these results, I neglected the subcategories with less than 300 total co-visits in a single day to reduce the uncertainty. So some of the results you have seen in the previous slide, like stationary product manufacturing, are ignored here, like the first here. And finally, I created a ranking table that shows the ranking of each subcategory in each of the 3 techniques. Now, the smaller the number is for a specific subcategory, the closer that subcategory is towards the fitness locations. These are the results I have created using network analytics on a specific day, which was February 24th, 2020. I also have results that I explored what people tend to do on the same day of their gym visit and what they do differently on the day they are not visiting the gym. 2 small examples of that were the figure with diet and weight reducing centers and the snack and non-alcoholic beverage bars. But I explored them much further, except from the examples you have seen here. So let's look at the examples again. So I created something like these 2 figures, but for all other subcategories. And I found these 2 to be interesting for motivation. So let's go back to the slide we were. So my goals now are to answer with more certainty these 4 questions. What exactly does each of the 3 techniques measure? How to use any of the results I have or the final ranking table to correctly order the subcategories? How to connect the results from multiple days? And what else is interesting to explore? Thank you very much for your attention, and I would be very happy to address any of your questions and to discuss any of your suggestions on the goal I have shown in the previous slide.
Cool. Nice presentation, George.